Dear participants, welcome back. Now we will start the second session of our invited speakers session. Now again, I would like to invite the chairman of the session, Mr. Brojne W. Olesen, to begin our session. Thank you.
Thank you. And in this session, we have three very good, interesting topics, and we have two distinguished speakers. And the first speaker, Wei Sun, is a very good person for ASRAE. He is the one who is giving a lot of his free time to work on different ASRAE committees, especially, of course, on clean rooms, which we're going to hear about here. But also he is on ASRAE's Society's nominating committee. And they are the one who is deciding who should be the next president and so on. So it's a very important job he has got there. And he is both involved in standards on the ASRAE level, but also on the ISO level. And as you will hear in the first talk, clean room is a specialty. So please, Wei Sun, the floor is yours.
First of all, I think Dr. Olsen's very nice introduction. As you know, Dr. Olsen is going to be incoming president in a year and a half. So he's my boss. Having my boss did the introduction for me. It was quite an honor. Thank you. And also my deep appreciation to the Turkish HVACR and sanitation organization, and especially our president, Dr. Erigan, for the invitation. And this is my first time in Istanbul and also in Turkey. And I spent quite a bit of time to learn a little bit about the history, culture about Turkey. And so this will be my very good experience to experience this in person. And my topics today, the first one will be for the clean room design, and most of them relate with the ASRAE and IEST current new development for clean room design and research. And the second topic will be for the US healthcare industry design, and especially for the environmental control for the infectious space control. So I think I have roughly about 45 minutes. And the first presentation was prepared for 2 hours training for IEST and ASRAE. So I tried to do my best and to squeeze a little bit and try to cover as much as I can. Once again, thank you for all. And basically, we will cover several major issues regarding the clean room design and also some new development. As we know, clean room technology has been very widely utilized for many industries, from semiconductor to microelectronics to university lab and automotive, aerospace, and many others. By definition, it is a special enclosed area. Its environment typically has the following control parameters: temperature, humidity, sound, vibration, lighting, and many others. Now, these are very typical for any commercial spaces. But for clean rooms, we also have another set of the control parameters. For example, air pattern, room pressure, particle contamination, including airborne, surface, liquid-borne, microbial contamination, electrostatic discharge, and a gas phase contamination. Of course, we have many process specifics need to be considered during design. Many years ago, US, we used a 209 standard. Since 2001, US and most of the world, rest of the world utilize ISO standards. And currently, I'm on the two committees for the ISO standards on behalf of USA. One is the -4, clean room design and construction. And another one will be a new standard called clean room energy conservation, which will be -16. Within about 2 years, it could be published. Based on the current ISO standards, clean room classes are defined in 6 particle sizes: 0.1, 0.2, 0.3, 0.5, 1, and 5.0 micron. In comparison between the previous US standards and the current ISO standards, previous one we have class 1 to 100,000, cover 5 channels, but ISO standards, they add 3 more classes, and also including 1 micron as the size. So if we plot them individually, the left was the US standard 209. The right is the ISO new current standard. If we overlap them, try to see what's the difference, and we may realize that these two standards, of course, they are not identical, but roughly equivalent on the certain classes and the particle sizes. And this is the 3D chart illustrate the definition of the current ISO clean room classes. One is the particle size, cleanliness class. These are the particle counts or particle concentration in the air. Current ISO standard cover 0.1 to 5.0 micron. Oops, pushed the wrong button. 0.1 to 5 micron. If larger than 5 micron, typically we call these as the microparticles. If smaller than 0.1, we call the ultra-fine particles. What are the key sources for particle contamination? We will consider external, such as outdoor air, because commercial building and clean room buildings, you always bring outside air for ventilation purpose. So outdoor air can bring contamination. Indoor transfer air between rooms, because clean room, we have a room pressure control. So particle always move from high pressure side to low pressure, to move from high concentration side to low concentration side. So particle can transfer from people, from work surface, and internally we also have raw and semi-finished material. We have liquids, and also room construction material. They all generate particles. For many HVAC engineers, one of the interesting focus is the airflow pattern. For clean room design, typically we have 4 patterns. The first is non-unidirectional flow. We have a seating supply through HEPA filter or OPA filter. We have a low sidewall return. We also have a unidirectional flow. Seating supply, raised flow return. Or combination of the first and the second, that's what we call a mixed flow. You have a seating supply, you have a low sidewall return, but within the clean room, you may have a small space, which has a higher air density for airflow to achieve cleaner class. And also mini environment. Mini environment basically is an enclosed environment, and it's very similar as a mixed flow. In other words, inside the mini environment, you may have a cleaner class than the surrounding clean rooms. floor arrangement. In all days, typically we have a ballroom type. In other words, a huge clean room, you even can play soccer over there. And in US, we still have many rooms like that, especially during the early age design. Also, we have a service chassis style. In this case, clean rooms designed in a linear or rectangular shape. They may share a common return chase. Also, the third type is meeting environments. Once again, large area you can design at a lower class, but for the most critical areas, you can design with a cleaner class. One very typical observation for clean room design is, if you're walking into a clean room, you can look at the seating HEPA filter or OPA filter percentage. You can pretty much judge what could be the potential cleanliness class for the clean room. Typically for ISO 9 up to ISO 5, HEPA filter will be adequate. The percentage could start from 5% up to 60, 70%. But if you want to design ISO 4 or cleaner class, the chance is you may end up with 90%, even 100% seating fully covered by HEPA and or OPA filters. In US practice, basically, ISO 4 is the dividing line. Cleaner than that, OPA can ensure room have a lower concentration. If lower than that, OPA may not make a major significant improvement, so HEPA is adequate. There are two also different types of the airflow HVAC design. One is what we call the pressurized plenum, or called a fan tower configuration. In this case, we have multiple stories for clean rooms. Oops, sorry. Clean room floor. Underneath is the return space. And below that could be the basement to house utility equipment. In this case, you have a return fan, draw the air. Below the raised floor, send the air up. Then you put a HEPA filter at the seating level, so the seating plenum is pressurized. Then clean air will go through the return air will go through the HEPA filters, so the discharge air will be much cleaner. So out of all the particles, or majority of particles can be blocked by the HEPA or OPA filters. The second type is what we call the fan filter type configuration. In this case, you do not see major return fans. Instead, you see many filter units. They have an enclosed fan inside of fan housing. So each of these boxes, they can actively draw the return air, then pass through the HEPA or OPA medias, so you can supply the clean filtered air into the clean rooms. So underneath could be still the return floor, and the basement you still can use to house process or utility equipment. So these are two typical types of airflow arrangement. One very important question right now facing ASHRAE, REST, and also our European counterparts is how to determine the quantity of the airflow. So let me give you some background information. First is the comparison with general purpose room. For commercial building, typically in the US, possibly in the rest of the world, 70–80% of the building air change per hour, possibly within 6 up to 25. Some could be higher, some could be lower. The purpose is to meet the heating, cooling loads and the ventilation load requirement. But for clean rooms, the airflow range typically is much higher. You may start with the 15, you may go up to 600 or even higher. People may ask why I need to go that high air change per hour. In addition to heating, cooling, ventilation requirement, another very important agenda is to dilute the particle concentration in order to achieve the cleanliness class. So clean room virtually is the dilution process. The more clean air you brought from the ceiling, the average concentration of the air, the particle concentration will be lower, so your cleanliness class will be better. Not many books want to use the word dilution. Sounds like it's a very energy non-efficient way, but unfortunately in the clean room industry, when US invent the clean room concept in late 50s, 60s, that was the major mechanism to achieve the cleanliness class. It is like a fish tank. In order to have a fish tank water cleaner, you either dump the old water, bring in the new tap water, or you drink and you bring the new water, the clean water. So the more clean water you bring in, the color of the water tank will be lighter, which means cleaner. But we do not have a color for air. So equipment, that's the only way to measure the air quality and the particle concentration. But since clean room utilize so much higher energy than conventional commercial buildings, so the energy saving potential is very high. As the IEST president-elect, and I'd like to share the background information in the US, how we decided what's the air change per hour for each class. And this was a table IEST published for almost 2 decades, before 2013. In this table, basically, IEST is saying, if you want to have an ISO 8, we recommend you air change per hour from 5 to 48, 7, 60 to 90. And if you want to design ISO 2 or cleaner, the chance is 360 or higher. And people may ask, what was the justifications for these numbers? And I'll ask the same question for the IEST previous leaders as well. You guys put this table used for so many years. What was your justification? The official answer was there was no justification. It was experience-based. And we locked all these experts in the room for 2 days and tell them, if you don't get a conclusion for this number, you cannot walk on from the room. So eventually, all these experts, based on their experience, they wrote down the numbers, then to find out what's the consensus behind. So that was the justification. And sounds not very scientific at all. And in 2015, IEST published a new guideline, and which based on mathematical model to calculate what could be the required air change per hour. So the new technology could be, you provide airflow rate as needed, not picking a number from a table. And this is very similar as we do in heating cooling load calculation. 20, 30 years ago, we used a single page of paper. We write on the numbers, then estimate what's the total cooling heating requirement. But now we have very sophisticated software, right? You can calculate what's the heating cooling requirement and what's the ventilation requirement. And you can rotate the building any way you want. But for clean room design, we are not at that level yet. So after 2015, IEST published multiple equations we call the modeling technology. And in this case, you may have a different HVAC configuration. And in old days, we use the cleanliness to decide what could be the air change rate. But this new modeling technology, you can calculate air change rate or calculate the cleanliness class based on multiple variables. One is, of course, air change rate. The other is the particle concentration inside the room, particle generation inside the room. And also the combined efficiency from filters inside the air handling units, HEPA, OPA filter efficiency, and also percentage of the on-site air, and also the on-site air concentration. Because if you locate a clean room in a very industrial, dirty, highly polluted industrial area, and you need to bring certain percentage of on-site air, and that may impact the final cleanliness class inside the clean room. So now you have a mathematical way to calculate, to estimate, and but this is still at the beginning stage. IST and ASHRAE TC 911 working together, try to produce more document and a guideline to support the design engineers to do a better design for clean rooms. Now with this mathematical modeling, you can analyze the effect of each variable on the final room concentration. One is to look at what's the particle generation rate for the impact to the room concentration, so you can mathematically analyze. You also can look at the effect of the final HEPA filter impact. And in this case, as you can tell, if you have a air change per hour below 100, the difference between HEPA and OPA filter make a very small difference. But if the air change rate over 100, OPA can make the room much cleaner. And so that's a very important discovery. Oops. Also, you can look at the combined efficiency of the filters. In typical air handling unit, you have roughing, intermediate, and the final filters, then HEPA filter at the room level. So you also can analyze the effect mathematically. Also the on-site air concentration impact. Because of the mathematical model, now you can analyze the significance of each variable to the final room concentration. So in other words, you can select equipment, machinery, furniture, room construction material at a low particle generation, or you can isolate and remove high concentration particle generated inside a clean room. In old days, we let the particle generate, and then we provide a higher air change rate to dilute these particles. But then the new trend is, if you can identify what are the major sources for particle generation, instead of let these particles migrate into the clean room, you capture them, you remove them. If it's simply particle contamination, you can use exhaust air with the HEPA filter, then on the downstream of the HEPA filter, which is still can be used as the return air. So you may not lose any air, but you can block this particle very effectively. And also to enhance the surface cleaning protocol, because if the surface particle is not going to be removed, this particle can become airborne particle under disturbance. And also design the entrance and the exit system more effectively, and also room pressurization. Typically, clean rooms are pressurized to prevent a particle, microbial, or chemical to migrate from on-site clean room into the clean room. So we talk about air change rate determination. Another very important characteristics for clean room design is what we call the air loop design. Typically in US, 400 CFM, maybe 300 to 500 CFM per ton in the international units, liter per second per ton, in a range of 150 to 250. And this is within the normal ratio. But for clean rooms, the air change rate is much higher. It's much higher beyond a single AHU can handle effectively. So if your air change rate is so high and your cooling load is relatively normal, then you will have a mismatch situation. A mismatch situation is that you may not have much, you only have a sensible cooling, may not have much latent cooling in order to remove or control room moisture level. So typically for ISO 6 or cleaner class, the airflow rate versus the cooling ratio may be beyond the reach of a single AHU can handle in order to avoid a mismatch. So in this case, multiple loops are often utilized. For ISO 789, typically we use 1 unit to provide heating, cooling, ventilation, and a cleanliness requirement. In this case, you have a 1 HU, draw the return air from the room, combined with outside air, filtered, heated, or cooled, then pump the air through the HEPA filter to the clean room. So this is a very typical configuration. Of course, HEPA filter typically are mounted on a ceiling rather than on a sidewall, but this is just a flow diagram. If you look at the real diagram, you may have different class clean rooms. You may share a common return air. Return air in the ceiling going to be drawn into the air handling unit, merge with the outside air and the supply air. You can do a reheat, you can do a humidification, then you provide the required air property to the clean rooms to achieve heating, cooling, ventilation, and air cleanliness requirement. So this is for the low-end clean rooms. This is a typical configuration, which is not much different as for commercial buildings or space. For middle-class clean room, ISO 4567, your airflow versus cooling load range is much higher. Could be 400 up to 2,500. In this case, you may want to use a primary and a secondary air loops. So in this case, you have a designated outside air unit. You have a return air, merge with the treated outside air, and so you use 2 units. Because the reason you use 2 units is that single unit will not be able to handle the latent load properly. The airflow rate is so high, and maybe 2 degree or 3 degree delta T, you already meet the room temperature requirement, but there is no condensation inside the air handler unit. In other words, moisture control inside the clean room is not available. If you go to the high-end clean room, ISO 1234, you may end up with primary, secondary, and a tertiary system. So in this case, you have a designated on-door air unit at the tertiary. You can have a return air 1, return air 2. The percentage of return air can be modulated based on the needs. And the goal is to use minimum mechanical cooling or heating to achieve the room conditions. So lots of control algorithms need to be developed to ensure the system can be optimized, not just mathematically, but also practically. So in this case, you use multiple air loops. So if you look at the airflow rate ratio between tertiary and the secondary, the fan for the secondary may be 2 times or 5 times more flow. The recirculation fan may be another 10 times bigger. So in other words, the fan for the tertiary is very small, basically just for on-door air. But the recirculation airflow rate is much, much higher. So that's another reason multiple loops can control room temperature, humidity better, and also utilize typically less energy to achieve the requirement. Now, as we talk about clean room utilize such a high airflow rate, energy consumption for clean rooms typically several times more than commercial, sometimes could end up at 50 times more. To achieve the cleanliness, you had to provide certain level of the air change rate to dilute. But for a typical working week, only 25% of the time is considered occupied time. Evenings, weekends, these are considered unoccupied time. In typical old design in the US and in many other countries, the industry utilizes constant flow year-round because they're afraid if they lower the air change rate, the room air cleanliness may drop below the specification. So to do that, they just run 24/7 year-round to maintain the same air change rate in order to achieve the same cleanliness. But now new technologies allow us to save much more energy during unoccupied time. Let's say if you want to design a clean room for ISO class, let's say 5, you have a continuous particle sensor in the room, which is almost like a thermostat, tells you the room particle concentration in terms of air cleanliness 24/7, real time. And as long as the room is clean enough, you don't need to provide more air than required. So that's the big potential for energy saving. So the strategy is to adjust or modulate the supply air rate to maintain the same or acceptable cleanliness based on continuous particle sensing, or sometimes could be microbial sensing, during both occupied and unoccupied modes, and which is only about 25%, 25% or less considered real occupied time. The rest, you can save a lot of energy. Typical two ways. One is to use staged ventilation. If you have a multiple fan wall, you can turn on few fans, turn off few fans to achieve different steps of ventilation level, or you can use a variable speed drive. Manual airflow adjustment. If you use fan filter units or recirculation fan, and you can adjust the fan speed to achieve the fan flow modulation. Or if you use a fan wall concept, you have many fans mounted on a single section. So you can turn on few of them, turn off few of them to achieve different level of the stage. This is a very simple flow diagram, and to indicate, to illustrate how to control the room particle concentration or room cleanliness level through typical AHU level control. So in this case, you may have two rooms, airlock room, clean room. You can have a multiple real-time particle sensor, typically is a laser. And you may have a controller. You also have variable speed drive in order to modulate, the speed of the fan filter units. So once this particle sensor says my room is already ISO class 5, then you don't need to speed up the fan. During the evening or weekend, once the room is unoccupied, this particle sensor tells you my room is very clean. I'm maybe ISO 4 or ISO 3, much cleaner. If you want to maintain as ISO 5, you have a chance to reduce the airflow. How much to reduce? The particle sensors will tell you. So this particle sensor is pretty much like the thermostats that we're using today. And thermostat tells you the room temperature real time. Particle sensors can tell you the real air cleanliness class at the real time. Many years ago, this device is much more expensive, so it's not feasible. But now it's become more cost effective. So sometimes the design firm can help the owner to reduce the energy consumption by this is part of your knowledge, this is part of your design consideration. Now for clean rooms, it is very interesting. Typically, we use the airflow to control the room temperature, humidity, right? We also use the supply air, return air, exhaust air to control the room pressure. But also we use a supply air to control the room concentration. So once you change the supply air flow, the impact for the room condition is far beyond temperature, humidity. You change the room pressure relationship, you change the room concentration in terms of the cleanliness class. So mathematically, they are mutually influenced, much more complicated than commercial space design. And that makes the clean room design engineer much more exciting and much more challenging as well. Construction material. That's the major difference between commercial spaces versus a clean room. ISO 6 or lower class, the wall system uses a different material. If a cleaner, typically use the aluminum surface. The paint for cleaner class epoxy is typical. And the wall panel typically is a honeycomb aluminum conductive finish. The low end, you can use a drywall with a coat. But for high end, usually the surface treatment different. And also the T-bar seating is different. And the cleaner class, because you put so many fan filter units, much heavier, and you also have a seal leakage issue. So sometimes use an 1.5 inch, sometimes use a 2-inch T-bar sealing. And also the floor treatment could be different. For the cleaner class, typically use a raised floor. I'm sorry. And less clean class, you can use the low sidewall return. And so that's the few key difference between the commercial space design and the clean room space design. I think I'm going to open the water. And below, I'd like to share a few ideas for renovation. Before and after, what's the difference? Basically, before was the ballroom design, and after is more like a narrower, multiple spaces to improve the airstream parallelism. And in old design, the exhaust, they don't have a real exhaust system. Particle generate into the space, they just use dilution to bring more air to dilute. But the new design, they have a canopy exhaust. Once they identify the major sources of a particle generation, instead of the particle to migrate, they capture them, then use a HEPA filter to block this particle, so on the downstream of this air, you still can recover as a return air. So in this case, the air change rate at the beginning was 385 down to 280, almost 100 air change per hour reduction. So you can tell much energy being saved. And the one below was the university chemical lab. Before was a chemical lab, after renovation, become a nano research lab, ISO class 3. And it's 100% HEPA upper seating. And use a teardrop lighting, because all the seating is occupied by HEPA. There is no place for lighting. So lighting is underneath of this 2-inch T-bar. And it's a raised floor return. Before, after, what's the difference we made? When I say made, we is engineers in the US. Before was a 380 or 50 air change per hour, ISO class 3. And on the right is the after renovation. At the beginning was a primary alone system, 1 unit. After renovation become primary and secondary. The total energy consumption reduction was about 65%. So with the new design concept, you really can reduce lots of energy consumption. This used to be a warehouse. After renovation, become a clean room. And it's a 22 feet retrofit space to be an ISO high bay clean room, ISO 3 class. And on the left and right side, these are the common, these are return chase. Return chase on site, this is the raised floor or the return air through the perforated floor, then back to the return chase, then drop by the fan into the seating space. Some other renovation design ideas. And this is the ISO 5 raised floor, large ballroom. And this is the photo underneath of these perforated floor panels. If you standing below, the room below this floor, you will see a lot of openings, circular shape openings. This allows the return air to down from the clean room space down to the subspace. So this uses a very heavy weight concrete panels, pour concrete. And this is also in the basement level, huge ductwork is made by stainless steel, and huge ductwork to move the air. And this is the, on the corner, is the, let's say, southeast corner. It's a mini environment space. The mini environment is ISO class 5. The surrounding space is ISO 7. And they put in the most critical process or effort, research effort inside this small space. So the surrounding area, you don't need to design so stringent in order to save energy. This is the sometime return floor panel. You may not need to use 100%. In this case, the return floor panel, the density is different. The reason for that is to house major equipment. Some equipment, they need to sit on the floor. So if you put a return grill underneath, the return path will not be very good. So not all the return floor need to be 100%. It's based on the classification and based on the application. I needed 2 days for the weather adjustment. From Michigan, USA was still cold, dry, and I come here, weather much nicer. But I need to take a few days to, even for the better, still need a few days to adjust. Now this is the common return. On the left is a clean room, on the right is a clean room. The return chase, you can put other equipment there. It's very wide. And these are the return panel from the clean room on the left side, draw into, then draw back to the seating level. This is the door. I know it's 45 minutes. So this is the leakage through the door opening or gasket is very important to minimize the particle migration. And sometimes people in the clean room industry use the sliding door versus the swing door because the longer of the door opening, more particle migration, because once you open the doors, whatever the pressure differential you have, it will drop to 0 very quick. And without the pressure differential, particle can move by concentration difference. Some other ideas. You can use a CFD to analyze the airflow. In US clean room industry also utilize lots of solar panel to supplement the energy consumption usage. Clean rooms typically is heavy duty, use a lot of air, but you also can design as like an office research park setting. So as a summary, during design phase, table method to determine airflow quantity may lead to significant over or under supply. Most time may be over, but if you simply use the tables, 80% of the chance you may overkill. So use the modeling method to establish a mathematical relationship between the air cleanliness and the control variables, and then identify the prioritized options to lower fan energy consumption. Select a proper air loop configuration, primary alone, primary, secondary, tertiary, between the supply airflow versus the cooling load. And also you can use the CFD to assist and to optimize design. During operation, there is a lot of chance to reduce the energy consumption. So for most clean room facility, occupied time is about 25%. The rest is considered unoccupied. Significant energy can be saved during unoccupied time. Basic option, monitor room particle concentration and use time-based reset. Time-based reset basically based on the time clock. During occupied time, you provide a high airflow rate. During unoccupied, you reset at a lower rate. What's the level to set based on the prior data or operation. So you can identify during occupied, I need this amount of air change rate. During unoccupied, I can reduce down to level B. A more advanced option is to use continuous particle sensing or even microbial sensor. Now, in US, Europe, we have a real-time microbial sensor to sense what's the microbial contamination. And with these sensors, you can use them as pretty much like a thermostat. And could be laser-based or could be multi-effects, the sensing system, as a feedback signal to control supply fan speed automatically. The key word is automatically. In other words, you do not want to use a thermostat, then you also manually adjust the variable flow or adjust the temperature, you let the computer do the work. So for clean rooms, of course, need to be controlled automatically. And also use the proper control algorithms and a strategy. So roughly about 15 minutes, that concludes my first speech on the clean room design. And most of these are a reflection of the recent ASHRAE IEST research and practice. Do we have time for question and answer? Okay. The chairman says, okay, so I'm open for a few minutes, maybe just 5 minutes, for some, no questions? Or we'll continue, okay? We can talk after the break, so there will be better time.
Yes, you will be here afterwards, and there you can put your questions. So let's give him a hand for the first talk here.
Thank you. So that's a good break for me when they load up the second presentation.
So your second presentation, remember, that will be a little shorter.
Much shorter, yeah. I try to control this within 35 minutes.
Thank you.
And now the second topic is regarding the airborne infection control space. Based on US CDC, Center of Disease Control. These are 4 categories in the healthcare settings are considered as the airborne infection space. Operating room, in Europe we call it operation theater. Airborne infection isolation rooms, protective environment, critical and intensive care. Many books available. ASHRAE book, 2013, hospital clinic design, AIA, FIG, ASHRAE, standard 170, CDC, and multiple source from CDC. We also, if you design pharmacy rooms, in the US, we also have USP 797. If you design military installation, you have a unified facility criteria design guideline. In the US, we also have a VA hospital system. They also have their own design manual. And of course, NIH, National Institute of Health, and also WHO. They all have this design guideline for these healthcare facilities, and many reference books and standards, including NFPA standards related with these facilities. IEEE. In US, we also have what we call the Building Design Code. International Building Code is one of the common. We have a building code, mechanical, plumbing, fire, energy conservation codes. When we design this space, typically the primary barrier is a personnel protective equipment, like respirators or gowning. The secondary barrier is what we call the engineering control, HVAC related or architecture related. Patient placement, layout, configuration, and a space environmental control. So our focus for the second topic is on the space environmental control. In US, we have, as we mentioned earlier, we have a AIA FIG standard. We have an ASHRAE. We also have a CDC. We have a VA and many others. And we put this into the same chart as a quick comparison. Operating room, isolation room. For isolation room, the anteroom, they are independent category. Total air change per hour requirement, what's the minimum outside air change, outside air in the total air. And so this is the summary chart. And this also is the pressure relationship. Ventilation requirement, 170. I think we are going to have a PDF for each attendees. So for those, I'm not going to go into the details, so you can have a copy, and I believe you will have my email address. If you have a question, you're welcome to send me email, ask a question. If I'm not able to answer, we have many ASHRAE, IST experts or other CDC experts. We can find an answer for you. Operating room. Typically, operating rooms, we design in positive pressure. The pressure could be 2.5 to 8 Pascal. That's actually very low, very minimum. Some design use much higher pressure differential. And HEPA filter is a typical, and UVGI light. And also the velocity requirement in the US typically is 0.3 to 0.5 meter per second. There are two different types of concept in the US. One is you see the HEPA filters above the patient bed. The other design style is use the linear diffusers. You may put a HEPA filter inside the AHU level or the filter bank. Then you discharge the clean air through these linear bars. Typically, in the US, actually, this is more common. Oops, I'm sorry. Oh. This is more common, but in old days, you find lots of design like that. The airflow arrangement is pressurized to let the air to push outside or to the restroom. 170 standard ASHRAE, they require to have a minimum 1 feet around the patient bed. And you can add additional filter supply air surround the surgical bed. But as the USA ISO representative, personally I have lots of interface discussion with the European counterparts in terms of their healthcare operating room, isolation room design standards and practice. The major difference between the US and the European countries, I'm not talking about one or two, talking about multiple countries. In US, we're still very conservative. Only 1 feet wider on both sides for the patient bed, for the HEPA filter coverage. Many of the current European standards require to have a larger coverage. not just cover the patient bed, but also cover the surrounding area for the surgical staff. And also, some European countries use a much higher air change per hour than US. US operating theater use 20, 25, sometimes maybe 30. Many European countries utilize 50, even 60 air change per hour. And also, some countries, they utilize the air curtain surrounded, try to provide a better linear parallel airflow to control the cleanliness above the patient bed. This is one of the typical configuration. I use the word called a 1/3, 2/3. In this case, they pretty much use the clean room design concept for the operating room. They utilize the fan filter units or recirculation system. You can provide up to 60 air change per hour above the patient bed, but you only use a 20 air change per hour for the cooling treatment. The second category is the isolation room. Isolation room, typically, of course, we design in negative pressure. The goal is to contain the contaminated air to migrate from inside to outside. And based on the US CDC guideline, there is one requirement is called the air tightness. In other words, you cannot make a room so loose. You have a construction tightness requirement to minimize, to ensure the room pressure and to reduce the dirty air migration. In US, we also utilize the blower door to test the air tightness, not just for the healthcare operation facility, also you can use it for residential, commercial, and also the clean room space. And in US, Canada, we have ASTM and the Canadian standards. You can calculate, use a computer to calculate what's the equivalent or effective leakage area. The airflow patterns for isolation room is is different. Typically, there is a 3 subcategory design in terms of the anteroom design. The first case is what we call the cascading anteroom. The second is bubble. The third is sink. For cascading anteroom, basically, the anteroom, the corridor has the highest pressure, then the anteroom, then the isolation room, then the restroom. So it's a one pass. The bubble design is you only have a supply air, you don't have exhaust. So the anteroom has the highest pressure, the pressurized air to the hallway, the rest into the isolation room, then exhaust them out. The sink anteroom design is totally opposite. Virtually you draw, you exhaust the air, and let the leakage air from the surrounding space to compensate the exhaust amount. So these are 3 different categories for the anteroom design. In clean room industry, we call the anteroom as an airlock room. And it's a very similar concept. The third category is a protective environment. It's a very similar design, concept-wise, as an operating room, but less stringent. The other category, the fourth, is critical and intensive care. And it's a much more straightforward. You can design positive or slightly negative, but most times people design the neutral or slightly positive pressure. You don't need to use a HEPA filter. 90%, 95% could be adequate. And these are the air change rate ventilation requirement. For the different areas inside a hospital and a healthcare facility. A very good design, I believe, you can have a design criteria for each room, write down all these major criteria as a protocol, and also the communication platform with the medical users. including architectural requirement, criteria, electrical, mechanical, plumbing, telecommunication, medical specifics. So each of these rooms, you can develop a sheet like this as your design criteria and also as the requirement when the owner to receive this room, try to see how much you achieve based on the criteria that you specify. Airflow diagram. Now this chart lists the multiple options. In no case you need to use all these options for a single project. This chart just illustrates some possibility. In this case, outside air, return air, you can have a return air 1, return air pass 2, and you can bypass the heating, cooling, humidification. What's the percentage? Based on the outdoor air condition, percentage of outside air, and also the condition of the space. So mathematically, or in the control algorithm, you can set up the control strategy so they can automatically adjust the percentage. You know, you can have a 70% to the pass 1, 30% to the pass 2, or any other percentage combination. You also can use these return fan as an exhaust. You close the dampers, so you can, instead of return some air, you can totally exhaust them. And also you can recover some sensible heat from the exhaust to use as a cooling or after cooling heating to reduce the energy consumption. And also you can use the entropy wheel to use the return or exhaust air to preheat or pre-cool the on-site air. But when you design this kind of facility, you want to design at a summer condition, winter condition, occupied, unoccupied, and anything between. So typically in US, we recommend to use a psychometric chart rather than use a hand calculation. So, so lots of these conditions can be specified in the sequence of operation. So in this case, you can use the exhaust only. Exhaust with heat pipe, exhaust with the entropy wheel, dual return path, or you can use 100% on-site air. If the room is being contaminated, you want to use the on-site air to quickly purge the air, and then you resume the previous configuration. Now let's talk about the room pressure control. 3 scenarios. If you want to design a room in positive pressure, typically you want to supply more air than return and exhaust combined to achieve a positive room pressure. So in this case, the offset supplies more than departing air. Entering is more than departing air. Departing air typically return exhaust. So to achieve positive, neutral, virtually the incoming and departing air at a similar or equivalent quantity. Negative pressure, you want to make sure the departing air is more than the incoming air. In US, typically we have several different rules of thumb methods. First is what we call the flow percentage. In this case, VA hospital is a typical example. If you want to design room in neutral pressure, incoming is equivalent to departing. 1 positive, 15% more. 2 positive, 30% more. 1 negative, 15% less. 2 negatives, 30% less. What's the justification? No, this is the experience base. This is a rule of thumb and rough design. The second category is what we call the flow differential. CDC, US CDC is the very good example. In this case, if you want to design neutral pressure, incoming is equivalent to departing. Positive, 60 liter per second flow rate more for incoming than departing. Negative, 60 liter per second less. But the problem for these rules of a thumb method is that each room may have different air tightness or enclosure, a fixed offset value without field adjustment capacity could cause problem in control. Because the 2 key elements to impact the room pressure design. One is the offset volume. The higher offset, the higher room pressure. The smaller pressure differential, the smaller offset, the lower pressure differential. The other very important element, which was typically ignored, is what we call the air tightness. For a very leaky room, you cannot hold as much pressure as you want. But for a very tightly constructed room, you can hold a much higher positive and negative pressure for the very same offset flow. So air tightness is another key variable in room pressure control design. The treatment of this offset flow defined what is the control strategy. In US, typically, we have 3 types: direct pressure differential control, differential flow tracking, and a hybrid control. Since I only have maybe 15 more minutes, I'll try to go very quick. Pressure differential control. And in this case, you may have an exhaust device like a fume hood or by safety cabinet. And you control the room pressure directly and let the controller to determine what should be the offset flow in order to achieve the delta P as you like to achieve. The second is the flow tracking control. In this case, the pressure differential sensor will be used as an indicator. And so in the controller, they have a prefixed offset flow. And once you want to achieve a certain delta P, you test in the computer to see what will be the needed offset flow. You embed it in the computer to achieve the pressure differential. But the challenge is that during the design phase, you don't know the air tightness because the room haven't been constructed yet. You cannot measure. So you had to put some numbers down in order to do the control design. The third type is what we call the hybrid, which is the combination of the first and the second. And I don't have enough time to go through detail because each of these subtopics could constitute another 2 hours presentation, and I don't have that. And now we talk about the room pressure control. One thing I didn't talk about is under what condition. When you control the room pressure, typically we refer to the condition that all the doors are closed. You cannot have a good pressure control if the door is kept open. So when the door is closed, no door is open, then you can control the room pressure. But the worst time for particle migration is not at the door closed condition. Because when the door is closed, you have a delta P, you can contain the particles to migrate to the cleaner space. But when you open the door, you don't have a delta P. Particle can migrate simply by concentration difference. And in this case, actually did a lot of tests in recent projects. They found that the particle migration is much higher than the time during the time that the door is in the closed position. So in actually, we call it the static control or dynamic control. Static control is the door is closed. On the door closed condition, dynamic control is, since you put a door, you had to use the door for traffic, for people, for material, for products. How can you minimize the particle migration during door operation? That's another challenging task. There's no other better way. There's 2 ways to do it in US and Europe, typically. One is what we call the airlock. In clean room industry, they use the 4 different types, but in healthcare, people use the anti-room. So it's very similar. And this is some CFD simulation. And it's an airlock room, or you can call this an anti-room. Gunning room, which is equivalent to the hallway, and a clean room could be equivalent to the surgical suite. And many of the CFD simulation is based on a static condition. You fix condition to see what's the impact. There's a new trend, especially for the research community, is to do a CFD on a dynamic condition. Door could be in operation, people could be in motion. Airflow rate from diffusers could be available. So in other words, you can vary this parameter to see what's the resulting impacts to many other air properties. So in this case, we put the color for the contaminated air in red color. You open the first door, we try to see how the contaminated air migrate or particles migrate from on-site into the anteroom. But if we open the door to the surgical suite too quick, without that much delay, the chance is some contaminated particles could migrate into the clean room or into the surgical suite. And this is the pressure field with the time. Typical design, we consider pressure is a constant, right? But once you do a CFD simulation or using very fast sampling speed for high-end pressure differential sensor, you can tell the pressure field is not constant. It's much more complicated than a single sentence can describe. And these are the particle migration. You open the first door, particle from the ground room migrate into the anteroom or airlock room. If the time delay between the first door and the second door is not long enough, once you open the very second door, some particle can migrate into the clean room. But if this is a contaminated air, the chance is the contaminated air could migrate into the operating room. Or if the ground room as the let's say, carry biosafety hazard, this biosafety hazard contamination could move into the operating room. That's not what you like. And a typical strategy to reduce the contamination is, of course, air change rate inside the operating room. The other is to increase the time delay between the first and second door. And so that's also very important. I don't have enough time. And so time delay basically allow you to use the air exchange inside the anteroom. Once you open the first door, the contamination will occur. You cannot prevent it. You can minimize them. Then use the air change to remove this contaminated air. Once the air in that room is clean enough, then you open the second door. And you can put the particle sensors. You can put even other sensors to indicate what's the quality of this air in these rooms. In Europe and many other countries, we also use pressure stabilizers, which is the counterweight or modelized counterweight of the spring-loaded relief damper. And but in US, it's not too common. It's more common in Europe and in other Asian countries. So Todd also mentioned a lot of the technology actually is working on that. But for the healthcare facility, especially for this space with the contamination or the infectious control, renewable energy, geothermal, solar, wind turbine, energy recovery, cogen, use of water, to cool, water cool compressor to recover the waste heat, energy recovery. At the building level, a building envelope, increase the tightness, and many other treatment. And I'd like to emphasize a few things. And one is use the sensor control natural daylighting and building metering system, occupancy sensor. And on the HVAC side, major manufacturers actually is working on very hard is the logical controlled ventilation and CO2 demand control ventilation, and also enhance the particle and microbial filtration technology to lower the on-site air intake. And one important thing is, it's also very interesting, is the very last item, what we call the AHU, discharge temperature dynamic reset of a VAV system. In old days, we either use the constant discharge temperature variable flow or use the constant flow variable discharge temperature. But currently, with the smart control algorithms, you can vary both as long as you know what's the nature behind that. And reset discharge temperature, adjust the airflow, you can happen at the same time. And as long as your computer model can predict what will be the situation after this adjustment. And a few samples for the US hospitals. And so that concludes my second speech. I think I'm still within your time frame, right? Yes. Thank you.
So, thank you very much. And please take the chance in the breaks to put questions and so. 1 minute, you're not finished. We have a small token of appreciation. Well, it's really not small, but even
Thank
if you gave 2 presentations, we only give you 1 of these.
Thank you. Buy one, get one free. Thank you. Okay, thank you very much.
Thank you. We'll go to the last presentation in this session. It will be given by Professor Marija Todorovic. She is a professor at the University of Belgrade and has been working with many societies like ASRE, Riva, giving her a lot of time to other interests. She has been also a judge in the solar decathlon, as I mentioned earlier. And one time in her very young career, she had to make a big decision. She was one of the top tennis players in her country, playing in Roland Garros and Wimbledon. And others she had to continue, and she would have been a millionaire now. But she decided to study engineering, and we are very happy you decided that, so we can hear your presentation here today. And the title of the presentation is Ozone and Climate-Friendly Urban Transformation via Renewable Energy Sources, Energy Efficiency, Modeling Predictive Control, and Smart Grid. So a broad topic you have to cover. Please.
Thank you very much for your kind announcement. Dear ladies and gentlemen, dear colleagues, it is my honor and my pleasure to be today here with you, and I'm grateful to organizer for inviting me. It's so dark here. Okay. So, you see, concerning the title, what is my topic? It is sustainability and renewable energy sources and building performance simulations, so technologies and knowledge and products which can be implemented really to try to save this world. But concerning the fact that exactly there are no technologies which can lead us to sustainability, we have to combine that and be aware that ethics is very important in all domains, and there is also ethics of sustainability. Oh, you didn't show me how I go down. So we go down. Let's see.
This one is forward,
Okay.
this one is back,
Okay.
and this is a pointer.
Oh, fine. Fine. Thank you. So there is a lot of talk on global warming, and there are also measurements and confirmation that climate is changing. But there is also mathematical theory on climate. It is very interesting that this theory was defined and all calculations done by one civil engineer, professor of Belgrade University, just when it was not yet a university, but just high technical school, Milutin Milankovic. And on his graphs, are visible ice ages, and those ice ages and periods when they are occurring are in very accordance with NASA findings. So it would be very interesting to put the features of current atmosphere, Earth, in his equation and see what would be the result. Weather extremes are definitely occurring, and for human comfort and health and survival, air conditioning is crucial. 2 years ago, we had in Belgrade even power plant, very powerful in water. After 2 years, it was again, several weeks ago, again, floods around Belgrade and many parts of Serbia. So again, weather extreme. There are also very urgent needs to do something with ozone depleting and to mitigate also from that way climate change. There is important assessment of impact of HCFC alternatives on global warming, and they have to consider both direct contribution of the alternatives as greenhouse gases and the indirect contribution of the CO2 emission from just energy required to power different system, HVAC, especially refrigeration. So the sum of direct and indirect emission of greenhouse gases represent this total equivalent warming impact, which is to be really taken serious. Then there are other extremes occurring nearly a year ago, even more, particularly extreme now in these areas. Political extremes, migration, immigration, countries, governments, understanding real need, countries and government which are just thinking on themselves and so on. So again, question of human ethics. There are needs, for example, in Serbia, or it was two borders, but now there are also west and north borders and south borders to act in the direction of resilience, somehow to help people to get just cover, to get food, to get dress, their babies, their children. And maybe most of that, I mean, shortage of fossil fuels, global warming, climate change, is partly result of this, what is for several decades, exactly starting from industrial revolution first, growing cities. But that's what was happening early when first industrial revolution is far behind concerning chaos and problems comparing with what's happening today. In Serbia, villages are dying. In China, the villages are dying. But in Serbia, growing is Belgrade, 2.5, 3 million. But in Turkey, you have the biggest city of Europe. We are in. And even more contrast is China. Villages also dying, and we were in Chongqing, where live nearly 30 million, 40 million people. Nanjing, you see here, we are their guest professor, they're tower building. If you look on all traditional buildings in all parts of the world, they are harmonious, they are harmonized with surrounding. They, for example, here buildings in villages in Turkey, Serbia, but the same is in Germany, Russia, US, China. They have a huge attic space, volume, to save them for overheating in summer, overcooling in winter. They have fine proportion between windows and non-transparent walls. So it's easy to add their solar, ground, geo-energy and get even zero, I say fossil, to be clear, zero fossil energy building. But in such cities, it is impossible. So this extreme intensive migration, which is under the way, growing cities, political, economical problems, and serious housing. So in order to conduct urban transformation and reach sustainable social and economical development, it is necessary to transform urban with suburban and rural areas integrally to enable a reliable approach to harmonious development, to reduce disparities in living conditions, which includes increasing accessibility to energy supply, suppressing pollution, and reducing CO2 and other greenhouse emissions, so to support growth of clean, renewable energy sources. People need same quality of life. So if we provide people with fine standard, the same quality and standard of life in city, they will stay in their villages and enjoy nature around that. Bjorn was using this slide also here. So these are energy saving construction country road maps. It is here, but what is important, that these road maps are smart, strategically, and concerning technology and industry and society be planned. So national energy efficient actions plans are very important. And in defining these plans, there is in use top-down analysis, starting from the top economy of the country, taking in account energy, environment, and economic models to examine market potential for utilize bottom-up, that is the next, synergies, offsets, and feedback effects, and represent the characterized technology-specific portfolios, subsystem, and so on. Here it is one example. It is Markov type, so top-down, starting from the energy balances of the governmental, state, country level, and then going down, taking all relevant factors, and starting from bottom analysis to the top, and that is exactly here the most clear. Economy, energy, that's top-down, availability, technologies, capital needs and technology deployment, constraint on imported mining, energy, demand for energy services, economy and society, energy consumption, ecological effects and emissions, and environment. So that's this top-down. And the other, so combining that one with what we have bottom, we say up, building performance simulation of energy in buildings, in neighborhood and cities. So, for example, there is Energy Plus, and starting with analysis of buildings, this combination, like it was studied in Brookhaven laboratory. Demonstration case study has been done for New York, and you can see how these surface temperatures as a result of energy use and energy thermal release to the environment are determined. Resources exhaustion, climate change, and also depleting are events and are processes which needs our help and solution. What we need? Combined heat and power production system, but based on renewable energy sources use. Biofuels, biomass energy, solar energy, thermal PV, photothermal conversion, geothermal wind, wave, and ocean, OTEC, energy, fuel cells, hydrogen produced using renewable energy sources naturally, low carbon energy technologies combined with improvement in end use efficiencies. I will just cover exactly kindly historically how the development in searching renewable energy technologies sources and climate and use of renewable and also different approaches to energy efficiency was occurring. The first, let's say, events or years when the world became aware about the exhaustion of energy and the problems which will, proceed, it somehow are correlated with the first and second Gulf War, Arabian Gulf War, and pretty soon